Scattering tomography using multiplexed X-ray sources. A CT scan can take between seconds and up to half an hour, depending on the body part being scanned and the physical properties of the patient. The waiting time for a CT scan can be as long as a month in some areas. Lowering the acquisition time can result with more patients being treated and scanned every day. In this research, we focus on a motionless CT scanner. Unlike the design of most commercial CT scanners, the motionless CT scanner doesn't contain a source and detector rotating together. The whole structure is completely static. How can we irradiate from all angles around the patient? This can be achieved by having a complete ring of sources and a complete ring of detectors surrounding the gantry. The sources can be switched on and off sequentially, virtually executing rotation. The motionless CT doesn't use an anti-scatter grid. This opens us to a new opportunity: multiplexing sources. Multiplexing sources means we irradiate from multiple angles simultaneously, and by that reduce the total number of acquisitions required. We define θt to be the set of activated sources in discrete time t. We can design θt to be as we choose. We can define it to be a single source at a time, and by so virtually simulate the rotation of current CT scanners. But now that we use a stationary CT scanner and don't use the anti-scatter grid, we're not obligated to use one source at a time and can use multiple sources. We can choose any combination of sources we wish. To account for scatter in the measurements, we use scattering tomography. Scattering tomography solves an inverse problem using a forward model and is formulated as an optimization problem. We formulate the loss function that takes a set of measurements and uses some parameterization of the scanned object denoted gamma. We minimize the square difference between images generated by the forward model and the measurements. We want to minimize it over all detectors and for every image in time t. To minimize this loss function, we take a derivative with respect to the density of each element in each voxel in the medium. We first compare delta, the global error term of the reconstructed mediums. Beta is the attenuation coefficient vector of all voxels in the medium. We can see the results of the linear estimation becoming worse as we multiplex more sources and increase the amount of scatter. In blue, we can see the results obtained by the scattering tomography. For up to 5 sources multiplexed, there is a minor degradation in reconstruction quality. From the graph, we can see we've retained the similar reconstruction quality while reducing the number of images acquired. These results might indicate we can shorten the total scanning time by 80%. The same conclusion arises when looking at the local error term epsilon. There is an increasing error in the linear estimation due to scatter. After the scattering tomography, 80% reduction in the acquisition time with similar results. We can see the reconstruction of linear and scattering tomography of a cross-section of the 3D medium when irradiated by 5 sources simultaneously. We encourage you to see other ICCP posters which present other aspects of the Cloud CT mission.